This is the second inorganic chemistry presentation. We'll cover chemical bonding among other things. Be sure to learn the chemical symbol for each of these common elements. Carbon is C, hydrogen H, nitrogen N, oxygen O, sodium Na, sulfur S, potassium K, chlorine Cl, calcium Ca, phosphorus P, and iron Fe. You should know how to calculate the number of electrons in each electron shell when given a chemical symbol and atomic number. Let me give you an example, and then I want you to see if you can go through the rest of this list and calculate each of the shells. Carbon is chemical symbol C, and the atomic number is 6. That means that it has 6 electrons. Remember that 2 will go in the K shell, and that leaves 4, which will go in the L shell. We start with the innermost shell, the K shell, and work our way to the outermost shell, or the N shell. Valence shell is a term that you should know. A valence shell is the outermost shell of an atom. For example, hydrogen has a valence shell of K, carbon has the valence shell of L, and sodium has the valence shell of M. If you look back at the last slide, what you'll see is the outermost shell of each of those elements that contains electrons is its valence shell. So the question arises, why is the valence shell important? The reason is because the valence shell determines whether an atom is reactive with other atoms or not. When the valence shell is full, the atom is unreactive. If the valence shell is not full, the atom is reactive. So let's look first at atoms with full valence shells. Remember, if the valence shell is full, the atom is unreactive. Helium has the atomic weight of 4 and an atomic number of 2. So that means helium has 2 electrons in its shell. So we draw the nucleus, put 2 neutrons in there, which we've calculated, 2 protons in there, and we know that there are 2 electrons. So we put the K shell, which holds a maximum of 2 electrons. The K shell is full, that means helium is unreactive. So if we look at the example on the last slide, how many electrons are in the K shell? And the answer is there were 2. So is the K shell full or not full? And the answer is yes, it is full, because remember, the K shell holds a maximum of 2 electrons. The third question is helium reactive or unreactive? Let's look next at neon. Neon has an atomic number of 10 and an atomic weight of 20. So there are 10 protons, 10 neutrons, and 10 electrons in neon. In the nucleus, you should place 10 protons and 10 neutrons, and then draw the first shell around the outside. Remember, that's the K shell. It will hold 2 electrons. So if I put 2 electrons in there, I'll be left with 8 electrons. So I draw the second shell, or the L shell, which holds a maximum of 8 electrons. I have 8 electrons left. They will go into the L shell. Since the L shell is full, helium is an unreactive atom. So you should now be able to answer these questions. How many electrons does neon have? The answer is 10. How many electrons are in the K shell? The answer is 2. And how many electrons are in the L shell? And the answer is 8. You should have determined, in the case of neon, that the valence shell is the L shell, or the second shell. Is it full? The answer is yes. Is neon reactive or unreactive? Since the valence shell is full, it's unreactive. This is argon, atomic number 18 and atomic weight 40. I rounded off the 39.9 and worked with 40. That means in the nucleus of argon there are 18 protons and 22 neutrons. It also means that argon has 18 electrons. So I begin to place them starting with the K shell. 2 go in the K shell, 8 go in the L shell, and that means that I have 8 left over, which go in the M shell. Although the M shell, or the third shell, holds 18 electrons, it always acts as if it's full when it has 8 electrons. So in this case, the third shell has 8, and it will act like it's full. Since argon has an atomic number of 18 and an atomic weight of 40, that tells you it has 18 electrons. In the K shell, there are 2 electrons. In the L shell, there are 8 electrons. And in the M shell, there are 8 electrons. So the valence shell is the M shell. Remember, the M shell acts full with 8 electrons, so argon is unreactive. We've looked at helium, neon, and argon and found that all three have full outer shells, where in the case of argon it has 8 electrons in the third shell and it acts like it's full. So this means that these three elements are stable or they are unreactive. Some atoms do not have full outer shells and are unreactive and bond with other atoms. One such example is sodium. You can see the atom sodium in the center of this slide. We want to look at how we form ions. An ion is a charged particle. Ions are charged because either they've lost or gained one or more electrons. When an atom gains or loses an electron, the number of negative charges is no longer equal to the number of positive charges. The first element we want to talk about that forms ionic bonds is sodium. In the center is a sodium atom, and on the right-hand side is the chemical symbol for sodium, which comes from the periodic table. Another atom that ionizes readily is chlorine. Since the atomic number of chlorine is 17, this tells you there are 17 electrons in chlorine. If I put 2 in the first shell, 8 in the second shell, I'm then left with 7, which I can put in the third shell. Remember, although the third shell holds 18, it will act full when it has 8. Chlorine only has 7. That means that chlorine is going to be reactive. Magnesium also forms ionic bonds. If you look at the atomic number for magnesium, you see that it's 12. That means that there are 12 electrons. So 2 electrons go in the K shell, 8 go in the L shell, and that leaves 2. And those go in the M shell. So when you ask, is the valence shell full? No, it's not. It will act full at 8, but it only contains 2. So we've looked at 3 atoms that will readily ionize. They are sodium, chlorine, and magnesium. The atomic number of sodium is 11. That means there are 2 electrons in the K shell, 8 in the L shell, and 1 in the M shell. Remember, the M shell acts full when it has 8, although it will hold 18. So sodium has only 1 electron in its outermost shell. Chlorine has an atomic number of 17. 2 electrons go in the K shell, 8 go in the L shell, and that leaves 7 to go in the M shell. Again, the M shell is not full, so this is a reactive atom. Magnesium has an atomic number of 12. 2 electrons in the K shell, 8 in the L shell, and 2 are left over for the M shell, which again acts full at 8, but only contains 2 electrons. If you refer to the chart on the last slide, remember that sodium has 1 electron in its outermost shell, and chlorine has 7 electrons in its outermost shell. Neither is full. The third shell will act full when there are 8 electrons. So the solution is to move one of the electrons away from sodium and put it in the outer shell of chlorine, and that's exactly what happens. Now the outermost shell of sodium is the L shell, and it has 8 electrons. The outermost shell of chlorine is the M shell, and it contains 8 electrons, so it's full. When you move a negatively charged electron from one atom to another, you create charges on each of the atoms. Sodium is now positively charged because it has 1 less negative charge, and chlorine is negatively charged because it has 1 extra negative charge. So sodium has 11 protons, or 11 positive charges, and 10 negative charges. That gives it an extra positive charge. Chlorine has 17 positive charges and now 18 negative charges, so it's got 1 extra negative charge. Here's another look at what just happened. 1 electron has moved from the sodium outermost shell to the chlorine outermost shell. So we've moved a negative charge from one atom to another. Now each of the atoms is charged. Since sodium lost a negative charge, it's Na+. Since chlorine gained a negative charge, it is Cl-. And the Na+ and the Cl- are attracted to one another, forming the molecule NaCl. Each atom now has a full outer shell, and Na+ is attracted to Cl- and again forms the molecule NaCl, or sodium chloride. Remember that magnesium does not have a full outer shell, and so we want to be able to fill the valence shell somehow. Based on what we just did, what do you think we might do in order to have a full valence shell for magnesium. As we saw before, we have the same problem with chlorine. It's got an outer shell that will act full when it has 8 electrons, but there are only 7 electrons in the outermost shell. So what might we do to fill this shell? If you said take one of the electrons from the outer shell of magnesium and put it in the chlorine on the right, and take the other electron from the outer shell of magnesium and put it into the chlorine on the left, you would be correct. This shows you how that happens. One electron leaves magnesium and goes to chlorine. The second electron leaves magnesium and goes to the other chlorine. The new molecule that's formed is known as magnesium chloride. With this movement of electrons, each of the 3 valence shells is now full. Chlorine has 8 electrons in its outermost shell, magnesium has 8 in its outermost shell, and the other chlorine has 8 in its outermost shell. Since we've moved electrons, we have disturbed the balance. Since magnesium has lost 2 electrons, it's got a charge of +2. Since each chlorine took on an extra negative charge or an extra electron, each chlorine now has a negative charge. Mg2+ and the 2 Cl- are attracted to one another, and the molecule magnesium chloride is formed. This again shows you the movement of electrons and the ions that develop, Cl- and Mg2+. The resulting molecule is MgCl2, also known as magnesium chloride. Magnesium chloride is commonly used to treat the roads for ice. This diagram shows a covalent bond between 2 oxygen atoms. Remember, covalent bonds are bonds in which electrons are shared and not transferred. 2 elements that form covalent bonds are carbon and hydrogen. Hydrogen has an atomic number of 1, so it has 1 valence electron. It still needs 1 electron in order to have a full outer shell, so it has the ability to form 1 bond. Carbon has the atomic number 6. Its valence electrons are 4 in number, and that means it needs 4 more in order to fill its valence shell. So carbon can form 4 bonds. Look at the diagram of carbon and the hydrogen atoms below. Can you see how each hydrogen has 1 valence electron and carbon has 4 valence electrons? So carbon can combine with each of these 4 hydrogens, and in that case, all would have full outer shells. Here are some common covalent molecules, and in the following slides we'll be drawing their structures. CH4 is methane, C2H6 is ethane, C3H8 is propane, C4H10 is butane, C2H4 is ethylene, and C2H2 is ethine. Before we draw each of these molecules, there are 2 important points you need to remember. Because carbon lacks 4 electrons in its valence shell, it has the ability to form 4 covalent bonds. And because hydrogen lacks 1 electron in its valence shell, it has the ability to form 1 covalent bond. Let's now draw each of these molecules. The first molecule is CH4 or methane. Remembering that carbon can form 4 bonds and each hydrogen can form 1, this is the only arrangement that we could make that meets both of those criteria. So carbon in the center and hydrogen on each side of carbon. Then you need to recount. Does carbon have 4 bonds? Yes, it does. And does each hydrogen have 1 bond? Yes, it does. Using the same criteria, how can we arrange these atoms in ethane, C2H6, to have the right number of bonds on carbon and to have the right number of bonds on hydrogen? So I have 2 carbon atoms and 6 hydrogen atoms that I need to bond to one another. The only arrangement that will work is to put 2 carbons connected to one another and hydrogens all around. Does each carbon have 4 bonds? Yes, it does. Does each hydrogen have 1 bond? Yes, it does. The bond between the 2 carbons counts as a bond for each of those carbon atoms. So this is the correct arrangement of the atoms in ethane. So we want to do the same thing with the molecule propane, C3H8. How can I arrange 3 carbon atoms and 8 hydrogen atoms so that each carbon has 4 bonds and each hydrogen has 1 bond? This is the only arrangement that will work. 3 carbons across the center, 3 hydrogens across the top, 3 hydrogens across the bottom, and 1 hydrogen on each end. Now count to be sure, but you should find that each carbon has 4 bonds and each hydrogen has 1 bond. This is the correct arrangement of atoms for butane, C4H10. 4 carbons across the center, 4 hydrogens across the top, 4 hydrogens across the bottom, and 1 hydrogen on each end of the molecule. If you count, you should see that each carbon has 4 bonds and each hydrogen has 1 bond. This is one arrangement for butane. In the case of butane, there are other arrangements that may work. Let's check and see what those might be. So far, all the molecules have been straight chain hydrocarbons. That means that the carbon atoms have been in a straight row. Is it possible to put the 4 carbon atoms in a ring, as in the diagram below? And the answer is no, because there would be too many hydrogens on 2 of the carbon atoms. Remember that carbon forms 4 bonds and hydrogen forms 1 bond. Look at the following slide. This is C4H10 in a ring. There are 4 carbon atoms and 10 hydrogen atoms. The problem is 2 of the carbon atoms have 5 bonds instead of 4 bonds, as they should. So what happens if we remove those 2 extra hydrogen atoms from the molecule? The problem then is we have C4H8 instead of C4H10. So butane cannot form a ring. One other possibility is instead of having the carbon atoms in a straight chain, we could have a branch chain, and that's what's drawn here. 3 carbons in a row, and off the middle carbon comes the 4th carbon. Can we put the hydrogen around and have the right number of carbons, the right number of hydrogens, and the right number of bonds around each? The answer is yes. If you check, there are 4 carbons, there are 10 hydrogens, and every carbon has 4 bonds and every hydrogen has 1 bond. So this is a branched chain, and it works for butane. Here are the 2 forms of butane that we talked about. The one on the left is the straight chain hydrocarbon. The one on the right is the branched chain hydrocarbon. In each instance, you have the correct number of carbons and hydrogens and the correct number of bonds around each. This is ethylene, C2H4. In this molecule, we run into a new problem. If we arrange the atoms as we have in the past, there are not enough bonds around carbon. The only way around that is to double bond carbon or connect them with 2 single bonds. In this case, each carbon has 4 bonds and each hydrogen has 1 bond, and there are 2 carbons and 4 hydrogens. This arrangement works. The bond in the center is known as a double bond. In the molecule ethine, C2H2, there is only one arrangement that will work, and that is the 2 carbons have to be triple bonded. 1 hydrogen is then attached to each carbon. So the carbons have 4 bonds each, and the hydrogen have 1 bond each. The prefixes of each of these hydrocarbons has a meaning. The METH stands for 1 carbon atom, ETH means there are 2 carbon atoms, PROP means there are 3 carbon atoms, and BUT means there are 4 carbon atoms. The suffixes also have meaning. The ending ANE tells you there is a single bond between carbon atoms. The ending ENE tells you there's a double bond between carbon atoms. And the ending YNE tells you there is a triple bond between carbon atoms. In the next few slides, we'll be talking about water, a very important component of our environment. Here are some of the characteristics of water. Water composes about 2/3 of the body's weight. It is necessary for chemical reactions to occur. It's known as the universal solvent, which means that more things dissolve in water than in any other liquid. It helps the cell hold its shape, and hydrogen bonds hold separate water molecules together. When we talk about water, we have to talk about 2 different bonds, the hydrogen bond and the covalent bond. A single water molecule, H2O, is held together by covalent bonds. Separate water molecules are connected by hydrogen bonds. Remember that the covalent is the strongest bond and the hydrogen is the weakest bond. Water is both cohesive and adhesive. Cohesive means that water molecules tend to stick to one another. Adhesive means that water molecules tend to stick to other substances. In this picture, you can see both cohesion and adhesion in these water droplets. These pictures show both cohesion and adhesion. On the left, it appears that a coin is floating on water. In fact, because there's surface tension, it doesn't sink to the bottom. On the right, it shows you water droplets that are beaded up due to cohesion and adhesion. Here is an important fact about water. Water has its maximum density at 4 degrees centigrade, which is a liquid. This means that ice is less dense than liquid water. That is why ice floats. It is a protective mechanism for organisms that live in ponds that freeze over during the winter.